Welcome to qnawire.
All right, on question 92, we're given a table with 6 different compounds, which I have drawn out here, and included their heat of vaporizations and their molecular weights. And the question asks us to explain really what's happening with the variance in the heat of vaporization with reference to, in part A, we're looking at the molar mass, or the molecular weight, we can think of it as. Part B, we're looking at shape. In part C, we're looking at polarity. And in part D, we're looking at hydrogen bonding. So in terms of molecular weight, in general, as we increase the molecular weight with other factors being equal, we usually increase the strength of the London dispersion forces, and therefore it's going to be harder to take more energy to separate the liquid, break those intermolecular forces, and go from a liquid to a gas, which is what we're doing when we're vaporizing here, this delta H of vaporization. So the stronger the intermolecular forces, the higher this heat of vaporization. But that's with all other things being equal. So the two to really want to compare for part A would be these first two. They are both just carbon hydrogen chains, straight chains. They don't have other atoms in there that can lead to polarity issues. So really the only thing involved, the only type of intermolecular forces involved in these first two molecules are London dispersion forces, because that they are nonpolar molecules, so that's the only thing that's going to be holding them together. So this is where molecular weight really becomes important. The molar mass, as the molar mass increases, going from 44 to 72, our heat of vaporization increases from 19 to 27.6, because again, the larger this molecule, the greater the molecular weight, the more polarizable it is. The more polarizable it is, the stronger the London dispersion forces. The stronger the London dispersion forces, the more energy it takes to separate out those molecules from a liquid to a gas, therefore the higher the heat of vaporization. In part B, we're looking at shape, and shape becomes important in terms of interaction between the molecules when they're trying to form these intermolecular forces. Straight chains, like these first two, can stack up on top of each other. They can form London dispersion forces all along the length of that molecule, and that's going to form stronger intermolecular forces than if they're interrupted by like a bent shape or a big molecule, big atom in the middle here. So we can see here, if we compare, for instance, molecules, this molecule here, we'll call this molecule, if we number them, let's do that. So this is 1, 2, 3, 4, 5, and 6. So for part A, we were really comparing 1 and 2. For shape, I would compare molecules 3 and 5. Again, we can compare those two because they have the same molecular formula, the same molecular weight. The only difference between them is their shape. Here, the bromine is on the outside. Here, the bromine is in the middle. And the straighter chain is going to allow for more interaction between the all along the molecule, as opposed to this bromine kind of starts to get in the way of forming intermolecular forces along the length of the molecule. It's cumbersome with this shape here. But with the bromine on the outside, this is going to have not only be, both of them are polar molecules, but this will also allow for stronger London dispersion forces because those molecules can stack one on top of the other. And that's why this number 5 has a larger heat of vaporization than number 3. When we look at polarity, we can look at, I would look at number 2. We could look at number 2 here. These and 1, these guys are completely nonpolar, right? So the only sort of intermolecular forces they have are London dispersion forces, versus basically all the other molecules are polar. And so they have not only London dispersion forces, but dipole-dipole, and 6 has London dispersion forces, dipole-dipole, as well as hydrogen bonding. So those polar molecules all have higher heats of vaporization than the nonpolar molecules, again, because they have, in addition to the London dispersion forces, they now also have dipole-dipole forces holding them together as a liquid. So that's more and stronger intermolecular forces that need to be broken in order to vaporize the substance. Finally, if we want to look at part D, hydrogen bonding, the only molecule here that can hydrogen bond is molecule 6. Remember, hydrogen bonding is between a hydrogen bonded to either an F, O, or N, and then the FO or N itself. And so the only one that has a hydrogen bonded to an FO or N is this guy right here with the alcohol. And therefore that this molecule can form hydrogen bonding in addition to dipole-dipole London dispersion. And hydrogen bonding is the strongest type of intermolecular force among molecules. And therefore this molecule has by far the highest heat of vaporization.